The subject of today's lab is oxidation and reduction. Now I know this is a subject which we don't come to until pretty much the end of 122, so let me say a few things about it so that we have the preliminary information that we need. First of all, let's define the two ideas here. Oxidation simply means loss of electrons. Now, the origin of the name oxidation comes from the fact that oxygen is very prolific in our environment at stealing electrons from other materials. This happens when a nail rusts and in a variety of other processes that occur in nature. So oxidation is given that name because so many materials in nature were found to be losing electrons, and typically the substance to which they were losing those electrons was oxygen. Then to contrast that, we have reduction. Reduction is gain of electrons. Now, the origin of that name probably comes from the fact that when you gain electrons, you are reducing your oxidation number. If you're in a -1 state and you gain an electron, you're now in a -2 state, or you've lowered your oxidation number. If you're in a +3 state and you gain 3 electrons, you are now at a 0 oxidation state. You have reduced your oxidation number. Now, sometimes these are called redox reactions, and when we have this occur, we call it an electron transfer reaction. We should note that these processes occur simultaneously. And the reason behind that is due to the premise that Ben Franklin laid out a long time ago, and that is that charge in the universe is conserved. If I do have a substance undergoing oxidation, if I do have a substance losing electrons, those electrons aren't swept under the rug of the universe. Some material somewhere had to gain those electrons or be reduced. And vice versa, of course, if a material is out to gain electrons, it must get those electrons from somewhere. It does not conjure them up out of thin air. So another material somewhere in the universe will be losing the electrons, which allows a substance to be reduced. Now, these processes, again, that we note there, and let's make this very clear, they are simultaneously occurring processes. You can't have oxidation without reduction, and vice versa. And with regard to the ability to induce another material to gain electrons, we will define what we call a reducing agent. And this will be one of the premises that we are going to be focusing on in today's lab. A reducing agent is actually a substance being oxidized. A reducing agent is losing electrons, but it is not just throwing those electrons into the universe's scrap heap. A substance that is a reducing agent is being oxidized, and in many instances, it is forcing a substance to gain electrons or be reduced, even though naturally this substance might not prefer to be reduced. If we refer to the periodic table, we will note that the majority of elements in that table are elements which do prefer to be reduced. Elements which prefer to be reduced are what we would know as metals, and the metals are listed here in blue in the periodic table. Also listed in here are other classifications, such as the so-called nonmetals and metalloids and other things as well. But metals, it turns out, there are other properties of materials that give them the ability to be classified as metals, but foremost among those is the ability to lose electrons or become cations when forming ionic compounds. Now, then the point would be, with regard to this idea of the reducing agent, is that if I have something like chromium or vanadium, it will definitely prefer to lose electrons to nonmetals such as nitrogen, oxygen, and sulfur. But if I have chromium and vanadium together with each other, these are both electron losing materials. However, one of them, it turns out in nature, has a better ability to lose electrons than the other. So it will have a better ability to force those electrons onto the other, whether or not the other really desires them. So what we would claim is the stronger this ability to give up electrons is, the better this material behaves as a so-called reducing agent, because it can force the reduction of the other material whether it would like to or not. Now, of course, one property that we could think of that we could tie this concept to directly might be something like electronegativity. Electronegativity, as we of course know, is the desire of electrons, of a material to draw electrons to it in a chemical bond. Now, then the more electronegative element we would think would be attempting to gain more of the negative charge. So there might be some connection in many instances with regard to the concept of electronegativity. Now, these quantities of electronegativity have certainly been quantified by chemists, but also these abilities to be reducing agents have been quantified by chemists and physicists in maybe a little bit more familiar terms to the layperson, as we will see going forward. Let's review the representation of a chemical reaction that we know as the net ionic equation. Suppose we have this particular reaction occurring. I have elemental solid zinc with copper 2 sulfate dissolved in water, and spontaneously, if you drop solid zinc into copper 2 sulfate, what occurs is the formation of zinc sulfate dissolved in water and elemental copper. Now, it turns out, though, that the reaction written in this fashion does not tell the entire story, certainly not from the oxidation reduction standpoint. So what we can note is that the zinc sulfate and copper 2 sulfate are electrolytes, and of course electrolytes don't exist in molecular form in solution, they exist as ions. So the middle equation I'm showing is what we would call the ionic equation for this reaction, where the electrolytes are shown in their dissociative states. Now, what I can then notice is, treating this chemical equation like a mathematical equation, that I have like common terms on each side of the equation, and they can cancel. So the sulfate is what we term in that regard a spectator ion, really not taking part in here the redox process. So I can eliminate the spectator ion from each side, and I can end up writing what we know to be the net ionic equation, or really where the action is in this particular chemical process. Elemental solid zinc reacts with copper 2 cations dissolved in water, forming zinc 2 cations dissolved in water and elemental copper. If we look at the net ionic equation from the perspective of oxidation and reduction, we note that the zinc is going from a 0 oxidation state in the elemental form on the reactant side to a +2 oxidation state on the product side, and therefore the zinc is losing 2 electrons. So in this process, the zinc is being oxidized. We note on the reactant side that the copper is going from a +2 oxidation state and ending up on the product side in a 0 oxidation state, so that the copper +2 is gaining 2 electrons. Now, this is going to be stoichiometrically true of any balanced equation. Not only should the mass relationships hold, or the number of zincs and coppers be balanced on both sides of the equation, now we will keep in mind that also the number of electrons being transferred between elements should be balanced in chemical equations. As a matter of fact, the balancing of electrons transferred in chemical equations is a trick that chemists have used for a long time to help them balance particularly tricky stoichiometric ratios in particular chemical equations. So what we can also then consider is that technically both zinc and copper want to become cations. In the situation like this, zinc is forcing copper in the +2 state to gain electrons, even though copper in the elemental form would seem to want to be a material that would lose electrons, but in actuality it really isn't. But we will see that quantified in some numbers upcoming here. But in any event, what we are seeing here is that zinc is forcing the copper to gain electrons whether it wants to or not. So we would claim zinc is a reducing agent for copper. Now, as a matter of fact, the opposite reaction is not spontaneous. If we reverse the reactants and products, or in other words, if I drop a solid piece of copper into a solution containing zinc +2 cations, it will not spontaneously plate elemental zinc that is neutral out and place copper cations into the solution. So what we say then, since zinc can force copper to gain electrons, that zinc is more active than copper, or I'm sorry, more correctly, zinc has a higher activity than copper towards being a reducing agent or forcing materials to gain electrons. We could make laboratory observation of the relative activity of zinc and copper in the following fashion. I take a strip of zinc, I place it down into a solution containing aqueous copper +2 cations. In this case, I have copper sulfate in the beaker. I let it sit in there for some period of time. I pull the strip out, and when I observe or make a note of the appearance of the strip compared to its original form, I will note that the part that was immersed in the solution has changed appearance, indicating some chemical process has occurred to it. What I would actually find beyond the observation, if I did some really careful analysis, is that this strip of zinc is now coated with copper. So what is going on as I place that strip of zinc in there is the electron transfer from the elemental zinc to the copper +2 cations to form zinc +2 cations and elemental copper. I can see the elemental copper from the change of appearance of the zinc strip when I remove it from the beaker. And the reason the elemental copper appears where it is because this is sort of, if you like, a heterogeneous reaction, meaning the two reactants are in different phases. I have a solid reacting with an aqueous phase material, so the surface of contact between this solid and the aqueous phase material is the point where the electrons are transferred. They are not transferred inside the zinc strip. They are not transferred away from the strip out in the middle of the juice in the beaker. The electrons are transferred right at the surface where the heterogeneous contact is between the two phases. So naturally then, the copper will be plated, as we say, directly onto the zinc surface. Now this is a spontaneous process, meaning the word spontaneous implying that it happens without any stimulus, external stimulus of heat, energy, electricity, or anything like that from us externally. We do not have to supply any external energy for this process to occur spontaneously. Now again, the point would be that we can make the observation that copper +2 is becoming elemental copper or gaining 2 electrons from the change in appearance of the strip. What we can't observe, but what we will surmise, is that in order for this to occur, that the zinc is coming off the strip and is replacing the copper cations in the solution. This has to be what is going on. Otherwise, remember what the solution would be doing is losing positive charge and would be building up a net negative charge due to the imbalance of sulfates present in the solution. So then spontaneously and naturally, as the coppers are plated from the +2 form to the elemental form directly on the surface of the zinc element atoms are losing 2 electrons and taking the place of those copper cations directly in the solution. One way in which we can use a tool to help us predict the relative activity of two metals compared to one another is using a numerical approach of the table of standard reduction potentials. This table lists the electric potential for all materials to gain electrons. So a reduction potential table tells the electric potential it takes to force a material to gain electrons. Now, in physics, electric potential has a name that your mom and them have heard of. Electric potential is voltage. So what we're saying, if you supply or receive a certain voltage of electricity from an element, it will naturally, in those instances, be able to be reduced or gain electrons. Now, as we will see here, some elements will actually give voltage off as they are reduced. Some elements will require voltage to cause them to be reduced. So these are quantified in this table known as the standard reduction potentials. Now, the term standard in the standard reduction potentials is a series or a set of physical states, or I'm sorry, mechanical states really, that allow us to define the particular point where these reductions are measured. The standard conditions where we measure the potential for a material to gain electrons are 1 bar pressure, which is very close to an atmosphere, it's 0.987 atmospheres in fact, and a temperature of 25 degrees C. So these are essentially laboratory conditions. Now also in the standard reduction potential determination, there is a standard concentration of a particular electrolyte in solution which may be gaining electrons. The electrolyte in solution should have a concentration of 1 mole per liter. Then if we measure the voltage either required or given off as a material gains electrons, we can call that the standard reduction potential for that material. This slide lists the standard reduction potentials of various materials. This list is by no means exhaustive. Scientists have rated the reduction potential of a wide variety of substances, metals, nonmetals, aqueous phase materials, all sorts of things have been studied to determine these values. Now notice there's an electrical potential, what we're claiming here, associated with the electrons that are being gained by the materials in these reactions. These are all electron gain processes. So they are all reductions. That's why we call it the reduction table. We call it the reduction potential because the measurement units that are used to determine the numeric value for this is electric potential, which is voltage. Now what you should note is that the values for these voltages vary from positive numbers to negative numbers. Now the point would be here that different materials have a different likelihood to be reduced. The more positive, as we will see, the more positive your value, the more likely you are to be reduced. Now, we see a large number in this list with negative reduction potentials. Those are materials which prefer to not be gaining electrons. They would prefer to be losing electrons. They would prefer to have their reactions reversed. So if you reverse a reduction potential, it becomes an oxidation potential. Now also, numerically, if you reverse the equation, you do the same thing to the sign of the voltage. So for instance, I show there that Pb plus 2 electrons gives elemental Pb has a reduction potential of negative 0.13 volts. Well, therefore, the reduction potential of Pb solid to give Pb plus 2 electrons would be positive 0.13 volts. Now, a few more things to mention about these before we go on. Again, there in the literature you can find tabulations of a wide variety of these values for materials. Secondly, when we list them, you'll note I'm listing E superscript 0. The little superscript 0 is an indication that these values were tabulated in the standard conditions. Again, those standard conditions being 25 degrees C, 1 bar pressure, which is very near an atmosphere, and 1 molar concentration for the materials. Another technicality by which these reduction potentials are determined is that if you're forming elements, you're forming an element in their standard state, how they naturally occur in nature. Now, you'll note though that we do list some reduction potentials for just gaining electrons without going to the elemental form. Believe me, these are numbers of this type have been studied for, as I mentioned, for a wide variety of processes. A very interesting case to note is that not all of these are forming metals in their elemental state. Some of them are forming other aqueous phase materials. As you can see, even some of them are forming gases. And of course, we can find the reduction potential of other gas phase materials too, such as F2. Now, notice very interestingly the so-called standard reduction potential for hydrogen. It is 0 volts. So the claim is that it takes absolutely no voltage to take an acidic solution and remove 2 protons from that acidic solution to produce hydrogen gas. That seems to be sort of a weird artifact of nature. To be honest with you, it is an assignment by humans. Humans have assigned the reduction potential of hydrogen to be exactly 0 volts, and we call this the standard hydrogen electrode. Now, why did we do this? Well, the reason behind why hydrogen has been assigned a value of 0 is so that we can scale all others relative to hydrogen. It's kind of like our temperature scales. We chose for Celsius the freezing point of pure water to be 0 degrees C. Then we measure other materials relative to the freezing point of pure water at 1 atmosphere pressure, and some have temperatures or will be in situations where their temperature is positive relative to that value. Some will be negative relative to that value. Here, the point would be that oxidation and reduction must occur simultaneously, so you can't literally separate the processes from one another. So let's just choose one reduction, set it equal to 0, and put it in combination with another material being oxidized, and all of the voltage which comes out of that process can therefore be ascribed to that other material. So this is akin to setting one side of the battery voltage equal to 0 and giving all the voltage to the other side, so that all others can be given an assignment relative to the setting of 2H plus 2E gives H2 gas at 0. So that was the reason for that determination. Let's note how we can use the standard reduction potentials to quantify activity. Here I have listed from the table the reduction potentials for lead, nickel, chromium, and sodium. And this is for their cations to gain electrons to become the elemental form. The more negative a reduction potential, the more likely the process is to be reversed. That's what we should recognize from this. As a matter of fact, the more positive a reduction potential is, the more likely a process is to be oxidized. I'm sorry, scratch those words, to be reduced. The more positive the value, the more likely you are to actually be reduced. The more negative your value, the more likely you are to be running in the reverse sense. The more likely you are to actually be oxidized. So if we are going to rate the metals on the right as their ability to be reducing agents, we would be choosing the one which is most likely to be oxidized. So what you do is you refer to the table, you find the one with the most negative value, and the more negative the value, the more likely you are to be oxidized. So the more negative the value, the more likely you are, or the more activity you will have towards forcing any other element to gain electrons, whether it wants to or not. So based on these numbers, given the fact that Pb has the smallest negative reduction potential and sodium has the largest negative reduction potential, then Pb will have the lowest activity among these metals, and sodium will have the greatest activity among these metals. So let's see the combination of the idea of laboratory observation of an electron transfer reaction with regard to using the table of standard reduction potentials to predict whether or not there would be a spontaneous reaction. Let's suppose I take a piece of lead and I set it down into a solution of nickel 2 chloride. So when I do this, the question would be, is there a spontaneous reaction in which after some period of time I pull the strip of lead out of the solution and I note that it is altered in appearance, indicating that it has been coated with the metal nickel from the solution. Now the implication to that process would mean, is lead more active than nickel such that the lead can force the reduction of the nickel plus 2, which is present in the electrolyte solution of NiCl2. So I turn to the reduction potential table. I dig up the reduction potential for lead and nickel. I find these two equations where the reduction potential for lead is negative 0.13 volts. The reduction potential for nickel is negative 0.23 volts. So to answer the question as to whether or not lead can reduce nickel, lead has to be a better oxidizing material being oxidized than nickel. And if lead is better at being oxidized than nickel, then it can give the electrons up that nickel will be forced to gain. That would mean that lead would have to have a more negative reduction potential. Remember, these values listed here are the values for these materials to gain electrons. And based on these numbers, the reverse of them tells me that nickel has a better thermodynamic likelihood of being an electron loser than lead. So nickel has a better ability to force lead to gain electrons than lead has the ability to force nickel to gain electrons. So lead has less activity than nickel, and as a matter of fact, if I was going to write the net ionic equation for these two, it would be Pb solid plus Ni plus 2 aqueous gives no reaction. Now, what I would point out to you is that the reverse reaction would be a spontaneous process. If I took a strip of nickel and set it down into a beaker of, say, lead chloride, let it sit there for a while, pull out the strips later, I would note that the nickel strip is altered by a coating of lead directly on the surface of the nickel. Again, the nickel goes on the surface because that's where the electron transfer occurs in the heterogeneous reaction. And also the nickel would be going into the solution as nickel plus 2 in order to replace the lead plus 2, which is being lost from the solution. So the solution remains electrically neutral by replacing one cation for the other. In that case, I would have a spontaneous net ionic equation, and it would be written nickel solid plus Pb plus 2 aqueous would give Pb solid and nickel plus 2 aqueous. Let's look at another example. Suppose this time I take a strip of aluminum and I put it down into an aqueous solution containing the electrolyte chromium chloride. As a matter of fact, we would technically call that chromium 3 chloride. Now, chromium 3 chloride is an electrolyte, meaning that it exists in the solution as chromium plus 3 cations and a spectator ion of chloride anions. So if I leave the strip of aluminum down in this solution long enough, when I pull it out, does it appear chemically altered? And if it does appear chemically altered, that would imply that chromium has been electroplated onto the surface of the aluminum. Again, I return to the table of reduction potentials. In the table, I find the reduction potential for chromium plus 3. I find the reduction potential for aluminum plus 3. And I note that the reduction potential for aluminum plus 3 is greater than the reduction potential of chromium plus 3. It's a greater negative than the reduction potential of chromium plus 3. The indication of these negative numbers, and now notice they're both negative. So the implication is that really neither of them really wants to be reduced. The spontaneous process would be these reactions in reverse. That would mean the aluminum and chromium giving electrons up, and those would have voltages associated with them. For the aluminum giving up electrons of plus 1.66 volts, and for the solid chromium giving up electrons of plus 0.74 volts. But with regard to aluminum versus chromium, because aluminum is a more negative reduction potential, it would be more positive oxidation potential and can force the chromium to be reduced. Now again, notice this number implies chromium doesn't want to be reduced. However, aluminum is so good at giving up electrons that it supplies enough electric potential to force this material, which does not want to really gain electrons, to actually do the electron gaining. So aluminum has a higher activity than chromium, and aluminum is a reducing agent relative to the chromium. This slide actually summarizes much of the information I gave on the previous slide. So again, let's note that both of these are large negative values. Aluminum is a larger negative value, which means it has more tendency to be oxidized. And if I would reverse that reaction, it would give me the plus 1.66 volts. And as Al is being oxidized, it forces the chromium plus 3 to reduce, even though, according to the natural tendency of it, it does not want to. So the activity of aluminum is greater than chromium, and the net ionic equation, which would result from placing a strip of solid aluminum into a solution containing an electrolyte of chromium 3 chloride, would be the net ionic equation you see below. Aluminum solid plus the chromium plus 3 cations will transform into chromium solid and aluminum plus 3 cations. So chromium will naturally electroplate onto the surface of the aluminum, and aluminum neutral atoms will replace the chromium plus 3 in the solution as aluminum plus 3s. A very important aspect of this redox process occurs if we separate the oxidation and reduction via a conductor. So what I'm showing in these cartoons below is, instead of putting a strip of aluminum down into an electrolyte of chromium chloride and having a spontaneous reaction where naturally I have a flow of electrons from the aluminum to the chromium plus 3, let me separate the two so that I have a chromium, I have a chunk of chromium in a solution of chromium plus 3, separated from a chunk of aluminum in a solution of aluminum plus 3. What I will note is that if I connect them via conductor and create a circuit, that I can still have the electron transferred from the aluminum to the chromium. This constitutes what we know by various names, including a galvanic cell, but what may be more familiarly known to your mom and them, this is what we would call a battery. This slide expands upon the galvanic cell and its definitions. Remember, I have a chunk of aluminum down in a solution of aluminum chloride, separated and by a conductor and connected to a chunk of chromium down in a solution of chromium 3 chloride. Now, these chunks of metals are known by two familiar names. They can be called electrodes, or they could be called terminals. Now, what spontaneously happens, as we see listed below, are the half cell reactions which occur naturally for each material. On the aluminum side, the aluminum is being oxidized. Remember, spontaneously the aluminum will lose electrons. That is a reversal of its reduction potential, as you see written there. It's written in an oxidation form as Al solid, giving Al plus 3 electrons. And the reduction potential has been reversed to a plus 1.66 volts. Now, on the left-hand terminal, I have the chromium coming out of solution and becoming chromium solid, and this requires an input, according to the sign of the reduction potential. In order for chromium to be forced to gain electrons, I'm going to have to give it 0.74 volts. So the cell reaction is the sum of the reaction of oxidation and the reaction of reduction. So you see the net ionic equation for the cell reaction listed there. And what you should always note is that when you are constructing a galvanic cell, you would always have one material being oxidized, and you will always have one material being reduced. You cannot construct a galvanic cell with two materials being oxidized. You cannot construct a galvanic cell with two materials being reduced. Always one of each is occurring. How do you know which one to reverse or turn around? If you're using a table of reduction potentials to generate the cell reaction, well, you always simply reverse the one so that when you put them together, they will give you an overall net voltage, as we see here. To find the voltage that this battery would put out, I simply add the electric potential of each half cell. I add the oxidation potential, which is plus 1.66 volts. I add the reduction potential, which is negative 0.74 volts, and I get a net of 0.92 volts. This, if we would like to think of it in other terms, I could call this related to the free energy available after the completion of this thermodynamic electrochemical process. This will be the energy that I can use to light a light bulb, to light a flashlight, to warm a stove up, or lift an elevator, or do any other mechanical processes that I would prefer. So as you can imagine, the technology and science of choice of materials to construct modern batteries that power our society are very important. There's a wide variety of aspects as to what materials you choose to make the terminals. Of course, cost effectiveness is one, safety is one, environmental hazard is another, lifetime is another, output voltage is certainly a big consideration. So the well-maturing industry of choosing the electrochemical processes that make modern batteries will continue to be a very important aspect going forward as we continue to use more and more batteries to power more and more things. Now let me discuss the activity series procedure that we are going to employ in today's lab. But before we do so, I want to make clear to you that there are various 124 sections that are all being taught by different instructors. Each instructor has his own ideas as to what they would prefer you do. Each instructor has a particular format in which they would like you to present their results. So I would urge you to be in contact with your individual professor to make sure it is clear exactly what you're expected to do with regard to the laboratory procedure and results that I am showing on upcoming slides. These slides refer to the instructions on page 48, Part A, Activity Series for Metals. What you first do is obtain a strip of lead, a strip of zinc, and a strip of copper. Get some steel wool and shine them up, meaning remove any material from previous experiments where there might have been electroplating on these strips, and also to remove any oxide coatings. Believe me, oxygen in the air is a highly reactive substance, so we want to get down to the elemental form of the lead, copper, and zinc. So we would remove the oxide coating from them in order to expose the elemental form of the strip. Next, get 3 small beakers and put about 1 inch of 0.1 molar zinc sulfate, 0.1 molar lead sulfate, and 0.1 molar copper sulfate into each. You will note that the 0.1 molar copper sulfate, by the way, has that distinct blue color characteristic of copper plus 2 cations in solution. This is true for any copper plus 2 solution. As a matter of fact, notice that the color for this copper plus 2 solution is not particularly dramatic, which again, what we learned from our colorimetry is some indication as to the amount of copper plus 2 in the solution based on the absorbance of orange light by that particular solution to reflect the blue color to our eyes. Now let's place a strip of copper down into the solution of zinc sulfate. So we sit the copper strip down in there, we let it sit in there for say 5 minutes, and when we pull it out, yeah, sure, it looks a little bit wet, but all it does is look a little bit wet. There is no obvious evidence that any change has occurred with regard to electroplating zinc out of the solution onto the strip of copper. So our conclusion from this would be something with regard to the activity of the copper compared to the activity of the zinc. Next, let's place a strip of zinc into the beaker containing the 0.1 molar copper sulfate. Let's wait a few minutes and let's make an observation on that strip. As the left-hand picture indicates, when I pull the strip of zinc from the solution of copper to sulfate, I note that there's a distinct difference in appearance of the zinc strip compared to what it looked like when I put it into the solution. So what I can conclude from observation is that there was a reaction between the elemental zinc and the copper plus 2 present in the solution. Now likewise, if I take a strip of zinc and put it into a solution of lead sulfate, leave it sit for a while, pull the strip of zinc out, make an observation on the strip, what I will note is that the zinc strip, when immersed in the lead sulfate, also has a change in appearance, so that there is a reaction between zinc and lead sulfate as well when I set that up. Now then I put a strip of copper down into lead sulfate, as I'm showing in the right-hand picture. What occurs when I put the copper into the lead sulfate and wait a few minutes, I pull the strip of copper out. Again, the bottom of the strip of copper appears to be altered, so I also conclude that there was a reaction between the copper and the lead. So again, there's a reaction when I put a strip of zinc into copper sulfate. There's a reaction when I put a strip of zinc into lead sulfate. There is a reaction when I put a strip of copper into lead sulfate. When I place a strip of zinc into either a beaker of 0.1 molar copper 2 sulfate or 0.1 molar zinc sulfate, and I wait a few minutes, pull the strip of lead out, I see no distinct change in the strip of lead compared to its original makeup. So with these results, I can make a table of my observations. In part A, 6 experiments were performed. I took 2 beakers, well actually I made 1 beaker of each. I took a beaker of zinc sulfate, 0.1 molar, a beaker of 0.1 molar copper 2 sulfate, a beaker of 0.1 molar lead sulfate. In turn, I put the other 2 metals into each of the 3 electrolyte beakers, meaning into the zinc sulfate beaker, I first put a strip of copper, then I put a strip of lead and made observations. Into the copper 2 sulfate beaker, I first put a strip of zinc, then later put a strip of lead and made observations. Then into the lead sulfate beaker, I first put a strip of zinc, then I put a strip of copper, and I made observations. According to the appearance of change of the strip, what I found was that placing copper into a solution of zinc sulfate, there was no reaction. Placing lead into a solution of zinc sulfate, there was no reaction. Placing a strip of zinc into copper sulfate, there was a reaction. But if I placed lead into copper sulfate, there was no reaction. Finally, placing either the zinc or the copper into lead sulfate allowed me to note that there was a reaction in both of these cases. So from these outcomes, you should be able to determine which of these metals is the most active, or which of these metals can beat the other 2, which of these metals is the weakest, meaning which of these metals can't beat the other 2, and which of these metals is in the middle, less activity than one, more activity than the other, because it can beat one and not the other. You should be able to discern this from this set of data. Again, students should refer to their individual professor's desires and taste, but for the students of Dr. Parkinson, you should certainly include the observation table in your report. You should, based on these observations, then write the activity series from least active to most active for the 3 metals, copper, lead, and zinc. Then what you should do in the case where the reaction occurs, you should write a net ionic equation demonstrating what that reaction is. Finally, what you should do for the 3 cases where there is spontaneous reaction, use the table of standard reduction potentials shown on slide 7 and calculate the voltage of the process, meaning to make one material being oxidized, the other being reduced. Use the table to determine what the voltage of those oxidations and reductions should be. Combine the oxidation and reduction, and it will tell you the overall voltage of that particular process. Now let's present a little background information on the so-called Faraday constant. The Faraday constant is named after Michael Faraday, perhaps one of the greatest scientists of all time. The reason why I have a particular favor for Michael Faraday is that he was probably, to my knowledge anyways, the last of the non-academically trained scientists. He didn't really have a formal training from an academic institution. He didn't go to a university to learn about science. He actually learned everything on his own. And as a matter of fact, he came to a lecture being presented by Humphrey Davy, a very prominent English chemist in the 1800s. He attended the lecture of him, and after the lecture, after the series of lectures was over, Faraday presented Humphrey Davy with a synopsis of the presentation, and it demonstrated deep understanding of the processes that Humphrey Davy was presenting to the public. And Humphrey Davy was so impressed that he hired Michael Faraday to work in his laboratory. And without question, the accomplishments of Michael Faraday far surpassed the accomplishments of Humphrey Davy, not only in the realm of chemistry, but also in the realm of physics, where he closely examined the behavior of magnetism and magnetic induction, which is the basis of the formation or the design of all electrical motors. Without Michael Faraday's contributions, none of that, well, at least it wouldn't have been possible as soon as it was. So let's now then turn to this idea of Faraday's constant. What Faraday's constant is the charge in a mole of electrons. Now, an individual electron has a charge of 1.6 times 10 to the minus 19 coulombs, which is the unit in which we measure charge. Now, first of all, we should point out this number for the charge on an electron is given a flavor, which I call flavor, meaning it's given a sign. So typically we see the charge on the electron as minus 1.6 times 10 to the minus 19 coulombs, whereas the charge on a proton is plus 1.6 times 10 to the minus 19 coulombs. Now, I should point out those are just assignments by humans in order to relate the difference in behavior that charges have with regard to the force they exert when put in proximity to one another, where they generate a field or action at a distance upon one another. We know that like charges repel or push apart, and opposite charges attract or draw together. So we have to be able to differentiate the magnitude of this push and pull they exert on each other as a push or a pull. So a plus sign and a minus sign is a convenient way to do that. Another thing we should note is that this charge on the individual electron is a real number and should have infinite significance, but of course we can't know it to infinite significance, but it has been measured very, very exactly to 9 digits of accuracy. And out to 9 digits of accuracy, it is known that the magnitude of the charge on the electron is exactly the same as the magnitude of the charge on a proton. And it is theoretically predicted that if they were possible to be measured to all digits of accuracy, they would be exactly matching out to infinite significance. And furthermore, that the magnitude of charge on an electron or a proton is the smallest amount of charge allowed in nature. You cannot subdivide that amount of charge into any smaller amount. Now you can combine individual electron or proton charges to build up negative or positive charge. You just can't make any smaller charge than these. Okay, so enough about the charge on an electron. If I now multiply the charge on each individual electron by the number of electrons in a mole of electrons, which of course is an Avogadro number of electrons, which of course again is a real number. If I multiply those together to 3 digits of accuracy, I get 96,500 coulombs per mole. Now I'm violating some of my pet peeve rules of significance there. I should probably write that as 9.65 times 10 to the 4 coulombs per mole electron to reflect 3 digits of accuracy. In actuality, of course, the charge on an individual electron is known to more than 3 digits of accuracy. The number of electrons in a mole is known to more than 3 digits of accuracy. So the Faraday constant is known to more than 3 digits, and a little later I will present it to a little more than 3 digits. So in conclusion here, the idea of Faraday's constant, and it's given a symbol F, is that it is the amount of charge in a mole of electrons, and since each individual electron has this small amount of charge, if I pile up an Avogadro's number of them, I get quite a significant amount of charge, totaling 96,500 coulombs. Faraday's constant is a very important factor or number when we begin to investigate the quantitative aspects of depositing metals or materials onto the surface of others through a process known as electroplating. So in electroplating, we use energy or electricity or run a current through a conductor, and we have immersed that conductor in a solution of electrolyte, and by supplying energy to that conductor, we can force the gain of electrons of the electrolyte in solution and coat the conductor with that particular electrolyte. So the reason that this is often done, and it is commonly done in industrial processes, is maybe to make a surface a little more abrasive or slippery, if we would like. Coat it with a particular material to do something like that. Maybe to make it less corrosive, like when we galvanize iron by coating it with zinc, or maybe we do it for aesthetic reasons to make it look prettier, like taking an iron ring and dipping it down into a solution of gold electrolyte, running current through it, and electroplating the gold onto the surface of the iron ring. So in our setup to determine Faraday's constant, we're going to set up one of these electrochemical cells. Now, really what we mean by that is a cell that runs by being powered. So you'll know we're going to be connecting a battery into a cell to supply electric potential or voltage, and it will feed a current through a conductor to strips of copper immersed in a copper sulfate solution and strips of zinc immersed in a zinc sulfate solution. Now this is connected in a completed circuit, as we see shown in the diagram, and there are 2 electrodes, if you like, immersed in the copper solution. There are 2 electrodes immersed in the zinc solution. One of them is an anode in the copper solution. One of them is a cathode in the copper solution. You'll notice that, of course, a cathode, as we mentioned on a previous slide for the galvanic cell, maybe I didn't say the words, but maybe I'll say them now. You can refer back to the information placed on that slide. The terminal where oxidation occurs is known as the anode. The terminal where reduction occurs is known as the cathode. So the anode is losing electrons, and that by definition is oxidation, of course. And when that occurs, notice that a terminal undergoing oxidation is losing solid and to an aqueous phase material. So the mass of an anode should be going down when you run current through it. On the other hand, let's look at the reaction of a cathode. At a cathode, we always have reduction occurring. So at a cathode, the electrolyte in the aqueous solution is gaining electrons and electroplating onto the solid metal form. So a terminal that is a cathode should be gaining metal, so it should weigh more during the process. So again, what happens is the anode is losing mass and the cathode is gaining mass during these processes that we're showing here. Let's do a sample problem where we attempt to calculate Faraday's constant. Now I know there are examples of this in the lab manual, but I'm not really crazy about the methodology that is used in the lab manual in order to come to this conclusion. What I prefer that you do is that you look at it from the point of view of dimensional analysis and stoichiometry. So let's suppose we have 41.25 milliamp current that runs for 2 hours, and we wish to know how much charge runs through the cell. Well, 41.2 milliamps, by definition, a milliamp is a coulomb per second, and also milli prefix means thousandth. So I have 41.25 thousandths of a coulomb per second. So if I convert that correctly to coulombs, it would be 0.04125 coulombs. Now for the time that the experiment was run, I ran the experiment for 2 hours. I need to convert that to the SI unit of seconds. So an hour has 60 minutes and a minute has 60 seconds. So every hour has 3,600 seconds. So I can do a conversion to find that 2 hours is 7,200 seconds. Now to find the total charge transferred to the electrodes during the experiment, I multiply the time that the charge was delivered times the current that the charge was delivered at, or I take 7,200 seconds times 0.04125 coulombs per second, and I find that 297 coulombs were delivered to the circuit. Now, let's suppose I have a zinc anode that I weigh, and I weigh it out at 7.875 grams. And after the 2 hours of running current through that electrode, I weigh it again, and it weighs 7.721 grams. Notice that the electrode has lost weight. This is because, being an anode, it is being oxidized, which means elemental zinc is becoming zinc plus 2 and losing 2 electrons. That's oxidation, loss of electrons. So the metallic zinc in the anode is becoming electrolytic, or an electrolyte zinc in solution, so the electrode actually will weigh less after this occurs. So I subtract the the final mass of the anode from the initial mass of the anode and find 0.1454 grams have been lost. And then by dividing by the molar mass of the zinc, I find that 0.00236 moles of zinc were lost. Now that I know the moles of zinc that were lost on the anode, I can determine from the stoichiometry of the half-cell reaction how many moles of zinc must have been transferred out of the anode as it loses those electrons. According to the stoichiometry, every time one zinc atom becomes a zinc plus 2 cation, 2 electrons are given off. So if 0.00236 moles of zinc were lost, and there are 2 moles of electrons transferred per mole of zinc lost, that means 0.00472 moles of electrons had to be given off during this process. So based on the number of moles of electrons used and the total charge transferred, I can find the charge per mole. According to the earlier calculation, 297 coulombs of coulombs of charge flowed through the circuit as it ran for 2 hours with 41.27 milliamps. Now that I have found that during that 297 coulombs delivered, there was also, based on the loss of mass of the zinc, converted to moles of electrons delivered. That was 0.00472 moles of electrons. I divide those moles into the coulombs of zinc, and I would find my value of Faraday's constant from this experiment at 62,900 coulombs per mole. Those results aren't particularly good, and as a matter of fact, I can calculate my experimental error in my experiment's Faraday constant. I will take the actual value minus the experimental value, and I will take the absolute value of that subtraction. Then I will divide by the actual value, and then convert to a percentage by multiplying by 100. And I will find that my experiment of the previous two slides had a 36.1% error in its determination of the Faraday constant. Let's now again turn to the procedure that we were to perform in order to determine Faraday's constant. Again, this procedure can be found in the lab manual, and it can be found on page 48, and we're now following through part B. Okay, so first I'm going to get 2 strips of copper and 2 strips of zinc, and as I did previously in part A, I'm first going to get some steel wool and clean them up in order to remove any contaminants from usage in previous labs, and also to take away any oxidizing coating. Next, I'm going to label each of the sets of terminals that I'm going to now use as 1 and 2. So I will have a zinc 1 and a zinc 2 and a copper 1 and a copper 2. The reason I do this is because when I run the experiment, one of them is going to be losing mass, one of them is going to be gaining mass. So in order to get the proper amount of mass lost or gained, I need to know which one is which when I'm starting the processes. I'm now going to take the 4 slabs of metal over to the balance, put each of them on there, and record the masses of these for later use. So let's suppose that I put these on there, and I did, and these are the masses I get for the 2 copper strips and the 2 zinc strips. I connect the 2 copper strips together in the following fashion. I take them and separate them by an insulator. Here I'm using cork, and then I wrap rubber bands around them so that they are attached to each other but not touching one another. Then I immerse the end of them in a beaker full of 0.1 molar copper sulfate. So I have 2 strips of copper, which I know the starting mass of, and I have separated them so they are not touching. And now I will place them down into a solution of copper sulfate. So I have the electrolyte, copper plus 2, in the liquid of the beaker, and I have metallic copper on each of the 2 strips. One of these strips will be the anode and one will be the cathode, depending on how I supply current to them or which way I hook the battery up relative to the plus terminal of the battery and the negative terminal of the battery. Now, what I do next is the same thing with the 2 zinc strips. I separate them by some insulator like cork, wrap a rubber band around them to secure them together, but make sure they're not touching. This time I take a beaker of zinc sulfate and I immerse the tips of the 2 zinc electrodes down into the zinc sulfate in a similar fashion to what I see here. Next, connect my electrodes of the zinc in zinc sulfate and copper in copper sulfate by conductors, as is demonstrated on the diagram on page 45 of the lab manual. I connect a meter in to monitor what current is flowing through the circuit, and I also take a ever-ready battery as a power supply, but before I complete the connections to the ever-ready battery, I need to start my timing, and I have to note the time when the experiment is started so that I will know the length of time that charge is being supplied to these two terminals. Simultaneously to when I complete the circuit, I note the time at which the experiment has begun. When I complete the circuit by connecting the battery and meter to the two sets of terminals, I should notice a deflection on my ammeter dial indicating the amount of current that is flowing. Now, I should be very careful in monitoring this current because it could fluctuate during the experiment. It could lower due to a drop of the juice in the battery, or it could lower due to jostling due to handling during the experiment. But what I'm going to assume here, and I did monitor this, as long as you don't touch it very much, and you have a pretty good battery, steady battery, I monitored a current of 12.68 milliamps running steadily during the time of my experiment. So this should be a number, again, that you should indicate in your write-up as to the current that was flowing through the circuit for the duration of the experiment. The picture on the left shows what the clock in the laboratory read as the time that the experiment was started. This, by the way, is in the morning. And the picture on the right shows the time at which the experiment was ended. This, by the way, is in the afternoon. So these numbers should be used to determine the length of time that the current was delivered to the electrodes. Now, during that time, the ammeter was monitored and noted every so often, and it was noted that the current stayed at the steady amount that was shown on the previous slide. I disassemble the apparatus after the experiment is over, and I carefully handle the electrodes that I used, mainly because the mass of the metal that is gained by the cathodes is a little delicate. It's not really well electroplated on there, I would say. So I'm a little careful with handling them. I allow them to dry because I don't want the amount of material to be tainted by the water if the strips are wet. So I allow them to dry, and then after they are dry, I weigh them again, and I get the following values for the final weight of the two copper strips and the final weight of the two zinc strips. What you should note when referring back to their initial weights is that one each of the two types of strips has gained mass during the electrolysis process. One each has lost mass during the running of current through the circuit. So here is what is to be done with the data gathered based on the pictures that you've seen on the previous set of slides for the Faraday constant experiment. Again, what you should do if you are not a student of Dr. Parkinson is you should refer to the instructions of your own professor to see how they want, what they want done, and how they want it reported. But for my students, what we're going to do is on our report, first we're going to include all the data provided in the pictures on the slides. Then we're going to use the clock photos on slide 36 to find the time that the experiment ran. You're going to need that in seconds. We're going to then use this information and the current supplied in the circuit from slide 35 to calculate how many coulombs of charge are transferred to each terminal. Now, then, what we will do is weigh or take, the weights of the terminals and subtract the weights of those terminals and report the change in mass that each terminal undergoes. Okay, so then what we will do after that is we will calculate the number of moles transferred using the molar mass of copper for the copper electrodes and the molar mass of zinc for the zinc electrodes. Find the number of moles transferred. Now remember again, one of them should be losing losing mass, and the other one should be gaining mass. So that one should be losing moles of element and the other should be gaining moles of element. Once we have the moles of matter transferred, use the stoichiometry of the half reactions. Let's be very careful here. Use the stoichiometry of the half reactions to note the stoichiometric connection between the moles of electrons transferred and the moles of matter either lost or gained. So you should use a stoichiometric conversion from the from the moles of material lost or gained into the moles of electrons that are lost or gained on each of those electrodes. Then what you should do is take the moles of electrons transferred for each terminal and calculate a Faraday's constant for each terminal by dividing the moles of electrons transferred to each by the total charge that is delivered to each. Now, each of them has the same total charge delivered to it. That is the value we calculated on the previous slide, but each of them should have a different number of moles of electrons lost or gained based on what you calculate on the previous slide. So you should get 4 individual values of the value of Faraday's constant. Please include those in your report. Then what you should do is average them together to get one final value for your Faraday's constant. Once you have this averaged value, use the accepted value of Faraday's constant, which is 96,485 coulombs per mole. Then calculate the percent error of the experiment with the data that you have been given.